Hey everyone, and welcome. Have you ever really thought about what stops you from slipping and sliding with every single step you take? Or, what actually keeps your car glued to the road when you make a sharp turn? Well, it all comes down to these incredible unseen forces. And today, we're going to dive right into the physics of friction and motion. So let's just jump right in with this question. What stops the entire world from being, well, a perpetually slippery mess? Like, imagine an infinite ice rink. Why isn't that our reality? The answer, in one simple word, is friction. It's this quiet, powerful force that governs pretty much everything we do, and we're about to break it all down. Okay, so here's the plan. First, we'll tackle friction, the unseen grip. Then we'll get into the difference between starting versus sliding. After that, we'll see what happens when you're moving through air and water. And finally, we'll tie it all together with the physics of turning. Let's get started. All right, first up, friction, the unseen grip. Now, it's easy to think of friction as just, this annoying thing that slows everything down, but really, it's the absolute hero of this story. It's the force giving us the grip, the traction, and all the control we depend on literally every second of the day. Okay, check this out. This is a really cool way to think about it. Whenever two objects touch, there's actually just one single contact force between them. But to make sense of it, we kind of split it in two. The part that pushes straight out, perpendicular to the surface, we call that the normal force. And the part that runs along the surface, fighting against any sliding motion, well, that's our friction force. And here's something that trips a lot of people up. You might think friction is all about how much surface area is touching, right? A bigger tire means more grip? Nope. It's really about just two things. First, the nature of the surfaces, like think sticky rubber versus super slippery Teflon. And second, the normal force, which is just a fancy way of saying how hard those surfaces are being pressed together. So a heavier box, it gets more grip. Simple as that. Okay, this leads us perfectly into our next section, starting versus sliding. And believe it or not, there's a little bit of hidden drama that plays out every single time you try to push something heavy. Turns out there are two different kinds of friction in the game. So let's follow the story of this box. Right now, it's just sitting there. Nobody's pushing it, so there's no applied force. And guess what? There's no friction either. It's kind of just dormant, waiting to be woken up. Okay, now you give it a little push, just a nudge. Instantly, our hero, static friction, wakes up, and it pushes back with the exact same amount of force. The result? The box doesn't move. It's held perfectly still by this invisible, totally adaptable grip. So you push a little harder, and static friction matches you again, getting stronger right along with you, just to hold its ground. But it's not infinitely strong. It has a limit. Right now, you're pushing at its absolute maximum. This is the breaking point. Any more, and there it goes. The box starts to slide. But look what happens. The moment it starts moving, the friction force actually drops. We've switched from that high peak of static friction down to a lower, constant force we call kinetic friction. And this explains something we've all felt, right? It is always, always harder to get heavy furniture moving than it is to keep it sliding across the floor. And this isn't just some abstract physics concept. This has real life or death consequences. Just look at this table for rubber on concrete, basically your car's tires. On a dry road, you've got a static friction coefficient of 1.0. That's your maximum grip for braking, for turning, for everything. But on a wet road, whoa, it plummets to 0.3. That's a 70% drop in the force that's keeping your car on the road. A huge difference. So far, we've only been talking about solid surfaces rubbing against each other. But friction happens everywhere. So for our next section, let's talk about moving through air and water. Here, we usually call the force drag or fluid resistance. But you know what? It's the same basic idea, just in a totally different environment. These graphs are just awesome for showing what's going on. The top line shows what would happen in a perfect vacuum. With no air resistance, an object would just accelerate forever, getting faster and faster. But the bottom line? That's the real world. You can see that with air resistance, the acceleration starts to back off, and eventually the velocity just hits a wall, a hard ceiling. It literally cannot go any faster. And that ceiling has a name: terminal velocity. It's that magic point where the upward push of air resistance perfectly balances out the downward pull of gravity. The forces are equal, so the net force is zero, which means acceleration stops. This is exactly how parachutes save lives, but it's also why elite cyclists and swimmers are so obsessed with aerodynamics and their body position. They are in a constant war against this fluid friction. All right, for our final section, we're going to bring everything together. We're going to apply everything we've learned to something we do all the time, turning a corner. So how does friction let you do that? How does it all work? Okay, so here's a core rule in physics. You just gotta know this one. To make anything move in a circle, you have to constantly pull it toward the center of that circle. It's called the centripetal force, which literally means center seeking. If you cut that force, say you're swinging a ball on a string and the string breaks, the ball just flies off in a straight line. It needs that constant inward pull to keep turning. So let's connect the dots. When you're in your car and you turn the steering wheel, what's the actual physical force that's pulling your car into that curve? What's providing that centripetal force we just talked about? And the answer is our hero from the very beginning, static friction. Yup, your tires, because of inertia, want to keep going in a straight line. But as you turn, the road grips them and provides an inward-pointing friction force. And that force is the centripetal force, pulling your car right around the corner. So here it is, the big takeaway. In a turn, the static friction force is the centripetal force. It's the same thing. This is what ties it all together. And think about it. If you try to take a corner too fast, you're asking for more force than static friction can give. The tires lose their grip and you start to skid. And remember how kinetic friction is weaker than static friction? That's exactly why skids are so terrifying and hard to control. You suddenly have way less force to work with. And I'll leave you with one last thing to puzzle over. We've spent this whole time establishing that the real force in a turn, the centripetal force, always pulls you inward. So why is it that when you're on a fast-spinning merry-go-round, you feel like you're being thrown outward? What's going on there? Something to think about. Thanks so much for joining.